The purpose of this tutorial is to show how to do related rates problems, and this is the kind of thing you'll see in an introductory calculus course. And there's lots of different kinds of related rates problems that you can do. So I'm going to show you 4 different kinds here, but there are certainly other types you could do. Anything that has relationships where something is changing could be a related rates problem. Okay, so we're going to start with the first example here. I'm going to work through it, show you how it's done, and then I'm going to summarize into a list of some steps, like a structure you can apply to related rates problems, and then we'll see how that works in 3 more examples. So in the first one here, we've got this 5-meter long ladder that's leaning against a wall, and for some reason the bottom of the ladder starts sliding away from the wall, and we're told it's sliding away at 1.5 meters per second, so there's a rate. So, and we're asked at what rate is the top of the ladder. Certainly if the bottom's sliding out, the top has to be coming down. So at what rate is the top of the ladder sliding down the wall at the instant when the bottom of the ladder is 3 meters from the wall? So that's the question here. So we're going to take a look at the given information. And so the given information is we're told the ladder is 5 meters long. So I'm going to start labeling on the diagram. So in some of these examples, I'll actually just label it on a diagram instead of listing all the different given info separately, like I am going to do here. So, and I'm not going to write out a let statement, but I'm going to call h the height of the ladder, and f the distance the foot of the ladder is from the bottom of the wall. So we're going to call that distance f there. So we're told that the f distance is increasing at 1.5 meters per second, and we're asked to find the rate that h is changing when the foot of the ladder is 3 meters out from the bottom of the wall. So that rate, find the rate h is changing, would be called dh dt. Most rates, the vast majority of rates, are with respect to time. So there's normally a dt in the bottom of the rate here. So we're told that f is increasing at 1.5 meters per second. So that means the rate that this side is changing is 1.5 meters per second, and we would call it df dt if that's the f distance. So we need an equation to represent the relationship between h, f, and 5 in that triangle. And because of the fact that this is a right angle triangle, we can use Pythagoras Theorem. And it's used a fair bit in related rates problems, not all of them, but anything involving a right triangle, you can use Pythagoras Theorem to find a relationship between those 3 sides. So we're going to differentiate both sides of this, and so the derivative of h squared, I'm using power rule here first, so we bring the 2 down and 2h to the first. I don't write the 1 if it's an exponent of 1. And I'm differentiating that with respect to time, so a different variable than h. So we would also multiply by dh dt. That's actually chain rule. So the first part is the derivative of the outside function, and then we multiply it by the derivative of the inside function. See, if I was differentiating with this with respect to h, I wouldn't bother write dh dh here, because dh dh would just be 1, and we wouldn't need it. So next, the derivative of f squared would be 2f, and then we multiply it by the derivative of the inside function f with respect to time, which is df dt. And 5 squared is the constant, 25 is just a constant, so its derivative would be 0. And notice that we can divide 2 into all 3 terms on both sides here, so if we do that, we get rid of the 2's, so we would just have this now. So I'm trying to find dh dt, so I want to isolate dh dt. So the first thing I'm going to do is I'm going to subtract f df dt from both sides, and then the h is multiplied by this rate I want to find, so I'm going to divide both sides by h. So I'm really just doing this. And of course those would divide out, and we would have dh dt is equal to negative f over h times df dt. Now I know f, f's my 3 meters. I know df dt, that's the 1.5, but I don't know h yet. So sometimes you have to find some unknown variable. So let's go back to Pythagoras' theorem, and in order to find h, I'm going to put 3 in place of f, because we're finding dh dt when f is 3. So 3 goes there, 3 squared is 9, 5 squared is 25. If we subtract 9 from both sides, we get h squared equals 16. And then to find h, we'll take the square root of both sides. So h is the square root of 16, which is 4. We'll use the positive root. H can't be negative 4, even though that's a square root of 16, because the distances here would all be considered positive only. So I can now substitute my 4 in here, and of course 3 in place of f, and the 1.5 in place of df dt, and evaluate that. So I would just be, I'll bring my calculator over here, so it will be negative 3 times the 1.5, and then divided by 4. Of course, if you want to do the negative 3/4 first, and then times the 1.5, that's exactly the same thing. So that's the rate. That's what it looks like. So dH/dt is negative 1.125 meters per second. So here's my concluding statement. The top of the ladder is sliding down the wall at 1.125 meters per second. Now, because I use this word down in this sentence, I don't need the negative here. You wouldn't say it's going down at a negative rate. That would actually mean it's going up. That would be a double negative. So down at 1.125 meters per second. So that's the idea. So I'm going to generalize all what I did here in some steps on the next page, and then we'll take a look at the other examples. So here's some steps to solving related rates problems. So identify the given information and draw a diagram if necessary. Sometimes you don't need a diagram, and we'll take a look at one of those later. And identify what rate is to be determined. And then you need a mathematical relationship between the quantities that you're given in the question, and something to differentiate. We use Pythagoras' theorem in the first example, but sometimes it's other things. So we'll take a look at that too. Number 3, once you get that relationship, you need to differentiate it, usually with respect to time. I'm going to use the word usually here, but I can't think of an example when it wouldn't be with respect to time. So it's like at least 99% of the time it's going to be with respect to time. Then isolate the rate you're looking for and substitute in the values you know. Sometimes you need to find one of the variables, like we needed to find that h distance in the first example, and then you can find the rate you're looking for. On to example 2. So we've got a bicycle has 40 centimeter tires, and of course you'd have to know is that diameter or radius. I'm going to use it to mean the radius here, but you'd have to make sure in a particular question, if you're told something's a certain size, what is it? Is it a diameter, radius, whatever it might be? So we're asked, how fast do the tires rotate for the bicycle to travel 54 kilometers per hour? So the rate we're looking for is the rate that the wheels are spinning around in order to travel 54 kilometers per hour. So I'm going to call x the distance between two places where the wheels rotated from one spot to another. And so I'm going to call n the number of revolutions. So we're going to be asked to find then dn dt, the rate that n is changing. Okay, how fast n is changing. And before we get into the math here, let's convert this into meters per second. It's kilometers per hour right now. So in order to convert 54 kilometers per hour into meters per second, we've got our 54 kilometers per hour. So let's do the kilometers first. There's 1,000 meters in 1 kilometer. So that's why so that converts the kilometers to meters. And then we need to go into seconds. We need, instead of hours, we need seconds. So there's 1 hour is 3,600 seconds. 60 seconds in a minute, 60 minutes in an hour. So 60 times 60 is where the 3,600 comes from. And if you do the math, we'll bring this over here. So 54 times 1,000. And then you see now times 1 over 3,600, so it means we're actually dividing by 3,600. So that gives me the 15. Now, if you're wondering why is it meters per second now, so if you look at, I'm going to write those rates out instead of meters per, meters over kilometers and hours per second. So you see what happens here. The reason it actually does the conversion is you see, this is just some algebra. This kilometer will divide it with this one. This hour will divide it with this one. And so the answer is meters per second. So there's the 15 meters per second again. Just to show you, if you're multiplying by 1,000 and then divide by 3,600, that's the same as, here's a shortcut for converting. See, 3,600 divided by 1,000 is 3.6. So that's actually a shortcut for converting from kilometers per hour into meters per second. If you just divide it by 3.6, you get the meters per second. Okay, so let's get rid of my writing here. So the given info is the radius of the tires is 40 centimeters, and we're asked to find the rate that they're changing when the speed is, see, instead of 54 kilometers per hour, the speed along the ground that the tires are traveling over is 15 meters per second. So that's a rate that we're given, and then of course we're asked to find the dn dt. Now, we need a relationship between the distance they travel and the number of times the wheels revolve. So the distance, and I'll just write this out, the distance between two places in time where the wheel has traveled is, and you see this is the circumference formula for a circle. So the distance it travels is the number of circumferences times the number of times the tires have gone around. Okay, so that's how you could get a relationship between the distance they travel and the number of revolutions. Okay, and again, n represents the number of revolutions. So this is what we're going to differentiate with respect to time. But first, we'll substitute the 40 centimeters in. And now I'm in meters per second, so this would be 0.4 meters. So I'm going to put 0.4 meters in place of r. 0.4 times 2 is 0.8. So x is 0.8 pi times n. So this is what we're going to differentiate with respect to time, both sides now. So the derivative of x with respect to time is dx dt. And see, the 0.8 pi is a constant, so the derivative on the right side will be the constant times the derivative of n with respect to time, which is dn dt. And I'm trying to solve for dn dt, so I would divide both sides by the 0.8 pi. So dn dt would be this derivative divided by 0.8 pi. So I'm just going to rewrite it up here with the dn dt on the left and that quantity on the right side. So there's nothing I need to find further here. I can just substitute in my values. dx dt is the 15 meters per second, and the 0.8 pi is going to be divided into that. So we get 5.9 revolutions per second, and so that's almost exactly 6. So if the tires rotate at 6 revolutions per second, the bicycle is going to travel the 15 meters per second, or 54 kilometers per hour. Now, if you want a nice expression for this instead of the approximated 5.97, if your teacher really wants those nice exact expressions, and lots of math teachers do, so the 0.8 is the same as 4/5. So we could actually then simplify this as it's 15 over pi times the reciprocal of this fraction. If you wanted to leave the pi with that, you could, but you don't have to. So the reciprocal of 4/5 is 5/4. And you see 15 times 5, and the numerator is 75, and 4 times pi is 4 pi in the bottom. Now, before we leave this one, if you're wondering why it's revolutions per second, I didn't put this in the presentation, but you see this 15 is actually meters per second. So yeah, I'll use this one here. So this is actually meters per second. And I didn't put the units with, you see this is actually 0.4 meters. So this is actually has a units of meters on the bottom here. So those divide out, and that's why it's per second, revolutions per second. So that's how you get the units. On to example number 3. So in number 3 here, different kind of question. We're asked, how fast is the radius of a sphere changing when its volume is changing at 300 cubic centimeters per minute? So we're given a rate, how fast the volume's getting bigger when the radius is 16 centimeters. So the given info would be that the radius is 16 centimeters. And see, this would be called the rate that the volume's changing. We would call it dv dt. So it's 300 cubic centimeters per minute. Now, and we're asked how fast is the radius of the sphere changing, so we're asked to find dr dt, the rate that the radius is changing with respect to time. Now, the connection between r and volume here would be the volume of a sphere formula, so you'd need to know that. So some of these related rates questions, you need to refer back to some geometry formulas, geometry measurement formulas. So the volume of a sphere is 4/3 pi r cubed. So this is what we're going to differentiate with respect to time, both sides. So on the left, the derivative of volume with respect to time would be dv dt. And you see, the 4/3 pi is just a constant, so the derivative on the right will be that constant, the 4/3 pi, times the derivative of the r cubed. So power rule, so the 3 comes down in front, that's what this 3 is here. We reduce the exponent from 3 to 2, we subtract 1 from it, and we multiply it by the derivative of r with respect to time, which would be dr dt. Now what happens with these 3's is these 3's divide out like that. And so on the right side, we just have 4 pi r squared dr dt. So dv dt is equal to that quantity. Now, it's dr dt we're looking for, so what I would do now is want to isolate the dr dt. So I would divide both sides by this 4 pi r squared on both sides. I'm writing it really tiny so it doesn't interfere with my next step here. So that's what we would do. So they would divide out. So dv dt over the 4 pi r squared is equal to dr dt. I'm just going to rewrite it up here with the dr dt on the left and the dv dt over 4 pi squared on the right. And so now we would substitute in our values. We were told that dv dt was 300, 4 pi times 16 squared. And so if you divide that, and maybe I'll bring the calculator over one more time here. So it's 300 divided by, in brackets, 4 pi, or 4 times pi, times 16 squared. So that's where I get my 0.093 from. Now again, units, why is it centimeters per minute? If you see, the 300 was cubic centimeters per minute, and the 16 is actually centimeters. So if you square that, that'll be centimeters squared. So those centimeters squared will divide into the centimeters cubed up here, leaving just a centimeter per minute. So that's why the units are centimeters per minute. So the radius is changing at a rate of 0.093 centimeters per minute. One last example, number 4 here. We're told that car A approaches an intersection toward the north at 15 meters per second, and it's a good idea to have a diagram for this one. Okay, something you can physically look at. And I'm going to add the given info to the diagram instead of writing it separately. So here's our given info on the diagram. So here's car A approaching the intersection toward the north. So at 15 meters per second, and we're told it's 120 meters from the intersection. So that distance is 120 meters, and it's approaching at 15 meters per second. So that means this distance is getting smaller at a rate of 15 meters per second. So that's why the rate would be negative. So I would call this dAdt because I'm calling this distance A. At the same time, car B is 50 meters past the intersection, traveling 10 meters per second west. So it's going this way, so 50 meters past. And so if I'm calling this the distance B, then dB dt would be the 10 meters per second. Now it's going away from the intersection, so this distance B is getting bigger, so that's why that rate would be positive. So I'm going to join these together, and I'm going to call that distance x. And you see, this is we're asked to find dx dt. So and the reason I use the times here is I could have just said 5 seconds later, I suppose, but 12:54:25 is 5 seconds after 12:54:20. So at that time, 5 seconds after this, are the cars getting close together, or is the distance between them increasing? Okay, and also, at what rate is that distance changing at the 5 seconds after? So this is a right-angled triangle here. So the relationship between the b distance and the a distance and the x distance is Pythagoras Theorem again. Okay, so we can use Pythagoras Theorem to get a relationship between a, b, and x that we can differentiate to find this rate we want to find. So x squared is equal to a squared plus b squared. So if we differentiate both sides, with respect to time again. The derivative of x squared would be 2x, and we would multiply it by the derivative of x with respect to time, which is dx dt. Derivative of a squared would be 2a times the derivative of a with respect to time, which is dA dt. And the derivative of b squared is 2b times the derivative of b squared with respect to time, which is db dt. Now again, like the first example, there's 2's and everything here, so we can divide out the 2's, and the 2's are gone. And so we're trying to find dx dt. That's what we're trying to find here. So it's almost isolated for dx dt. We would just have to divide both sides by x, so it would divide out. So dx dt is this whole expression here divided by x. And I know a, I know b, I know this rate, I know this rate, I just don't know x, what this actual distance would be. So I do need to find that. So we can go back to Pythagoras' theorem and substitute the 120 for a and 50 for b and find what x is, what the actual distance between them is at this 5-second later time. So 120 squared is 14,400, 50 squared is 2,500. We add those together, we get 16,900, and then we take the square root of both sides, so we get 130. So this distance right here is 130. If you know some Pythagorean triples, you might recognize this is actually a 5, 12, 13 triangle, or a 50, 120, 130 triangle. So that's why that worked out to be a nice whole number. So we can now substitute in our values. A is 120. dA dt is negative 15. The b is 50 here. dB dt is the 10, and we just found that x is 130. So when you go to evaluate that, make sure, okay, so on top we've got 120 times the negative 15 plus, 50 times 10 over 130. So dx dt is negative 10 meters per second, same units as these rates would have here. So the distance between the cars at 12:54:25, 5 seconds later, is changing at a rate of negative 10 meters per second, and that negative, since the rate's negative, that means the cars are actually getting close together at that point in time. So that's the interpretation of what the negative actually means. And that's because the car that's actually, probably because the car that's going faster is actually going towards the intersection. The one that's going slower is the one going away. So at this point in time, they actually are getting closer together. And that's the end of the tutorial.